Hello, this is Tyler Moore from the University of Tulsa, and I'll be continuing our introduction to information security by talking about security threats. So here's an outline of what we'll talk about. Essentially, we're going to look at different ways in which the assumptions of our threat models get violated for attacks to succeed. And this works at the system level, when attacking cryptography systems, and also how we think about attackers and defenders' behavior. And we'll wrap up with a brief discussion of how we might counter those threats. So here we have our diagram where we've previously talked about how we developed these defenses to help protect confidentiality, integrity, and availability. And then what we're talking about today are these security threats. So the threats to those defenses that we put up in place. Essentially, you can think of all security threats as assumptions gone awry. And what that means is that whenever we've done our threat modeling, we think about what we expect the attacker capabilities and functions to be. We don't account for everything. And so at the system level, this can be a violation of the assumptions of the engineers. For cryptanalysis, it's violating the mathematical or physical assumptions that are made in the design of the system. And then when it comes to people, well, it may not be a surprise to you, but computer scientists aren't the best at thinking about how people behave. And so frequently attacks succeed when the assumptions that designers make about how attackers will behave and how the defenders will behave are violated. So, privilege escalation attacks. Now recall that operating systems enforce access control mechanisms by separating privileged data and programs from normal files and processes. You have the super user who's granted access to the more sensitive operations, particularly those related to the operating system, like installing new programs. And a privilege escalation attack is a general attack where the attacker is able to take on the role of a super user and gain privilege that he otherwise was not entitled to, and that allows them to carry out unauthorized actions. So why is this such a big deal? Well, when you think about a threat like malicious software or malware that will install a bug that will track all of your communications, well, you need to be able to install the software to make that work. And so if you have a privilege escalation attack, that allows you to take a normal process and install this malicious software without the user's consent. And adversaries regularly exploit bugs to carry out attacks like these. So let's talk about how those attacks work. First, we'll go through an example at the system level, which is buffer overflows. So here is some example code written in C that's just trying to parse some input, and then it creates a local variable of a character array, which is a string up to 1,000 bytes long. So it allocates up to 1,000 bytes for the input string, and then copies the input message into that array, and does some more work. The thing to know about C is that strings are actually these arrays of bytes, and so you have, say, string, or you have the phrase blank TEST, which gets encoded using the hex values shown there. So that's all well and good so long as you only have an input that is as big or smaller than the input size you've allocated. So the way this works when it gets implemented sort of at a lower level is that you've got this sort of this is a visual representation of address space, and so your memory, you've allocated a chunk of memory. So we've allocated 1,000 bytes for the temporary array. So we have sort of the address for the starting and ending position indicated there. And then after that, just naturally, the compiler is going to put in a return address that will return control to jump to somewhere else in the memory. And the return address should be privileged. And so the problem is that the way things are working in C is that the string copy function doesn't know the size of the destination buffer TMP that you're copying into, and so an attacker can come along and overwrite the return address, say by providing an input size that exceeds what's been allocated. So he could say, in this case, the 1001st to 1004th character is the return address, so it provides an input that's 1,000 characters long of junk, and then the next 4 characters indicate a return address that would grant control to the user. So the user provided code gets executed with the privileges of the host program and allows the control to shift to some malicious code, which is actually located inside the local variable itself. So you then can execute code that previously would not have permissions to execute and say do bad things. So these buffer overflows have been known for decades, and yet they're still a problem because people continue to write programs in C for efficiency's sake. So more modern programming languages don't have these memory allocation issues like Java and Python, and yet so much of what's out there and what's still being developed today is written in C. So it continues to cause problems. So another way of looking at how inputs can be manipulated for an attacker's advantage, but now thinking about the web, is something called cross-site scripting. So let's say we have 2 clients who are both interacting with a web server that's, say, hosting some user content that's been created like a web forum. And so client B can come along, post a user comment, and just say and post it to the web server. And then client A might come along and want to interact with that web server and retrieve the comment. And to do that, first things first, the way things work on the web is you'll open your session. The web server will send a cookie to the client, which is used to help identify that client and provide a personalized experience on the website to the user. But the problem is that this cookie has to only be associated with this client. No other client should be able to obtain that cookie, because if they were, then they could then impersonate the client. So so he'll present the cookie to access the user-generated content, and that's all well and good, provided that the content that the client B posted was not malicious. But in comes our attacker, who instead of posting a nice comment, posts some code, posts some JavaScript. And what does this JavaScript do? It says document write, and then it says image source, so it's going to load a URL at some malicious website like mal.ru, and then what does it do? It says encode URI document cookie. So it's actually going to request the cookie that the user submits, and then send it off to mal.ru, which is something out of the attacker's control. And if client A blindly trusts the input that came from attacker B, he could then inadvertently execute that code in its client, which would then pass the cookie to the destination under the control of the attacker. That would grant control of the session ID, and then he could then impersonate A by presenting the cookie. So cross-site scripting is another example of sort of unexpected inputs being used to cause problems, and it goes back to the von Neumann architecture, where we're treating code and data as essentially the same sequence of bits. Our last example of this is code injection. So this is a classic XKCD comment. And what does it say? Well, hi, this is Sean School. We're having some trouble. Oh dear, did he break something? Well, in a way. Did you really name your son Robert, quote, parentheses, semicolon, drop table students, semicolon, dash, dash? Oh yes, little Bobby Tables. We've lost the student records, because what happened here is the expected input, which was a name, actually ended up escaping and producing a malicious SQL statement, drop table students, which would then, do as you might expect, drop a database table. And so this is called a SQL injection attack, and these are also quite pervasive. And the common thread here between this and cross-site scripting and even buffer overflows comes down to input validation. You need to validate the data that's going to be provided and not trust it, and so that you can ensure that a malicious actor can't insert some code that's going to do bad things to you. But again, this is a violation of the assumptions of how you expect things to work. You expect data inputs to be data, but if they're not, bad things can ensue. Another related threat that's worth mentioning is something called drive-by download attacks. And so what these do is that an attacker somehow gains access to a web server, and through compromising it by, say, stealing a password or some other means, so exploiting a vulnerability, and then add some code to that web server, which then whenever a browser interacts with it, it will execute that code and then try to infect visitors to that website. So here's some example code. It's an iframe, which is an included frame where you're loading an external content, in this case the URL evil.ru/keylogger.exe, and we're loading this in an iframe that's 1 pixel by 1 pixel large. So it's somewhere on the screen, but the user can't see it, but nonetheless, the way browsers work, it's going to execute. Then bad things ensue. And again, this is violating the assumption that you would not expect that a website that someone's going to visit would have this malicious content loaded onto it. And the way browsers work is they tend to trust other domains than the domain you're visiting, which is not always a good assumption to make. So think about some of the security defenses we've come up with, and my question to you is, how could you envision encryption helping prevent drive-by download attacks or the code injection attacks we've talked about? We can discuss that in class. Okay, so we've talked about system assumptions. System assumptions being violated for the purposes of security threats. Now we'll talk about cryptanalysis. And so cryptanalysis has a long history. It's been used for decades, really actually dating back to the beginnings of cryptography, where the goal of cryptanalysis is to descramble some ciphertext, some encrypted communication, and obtain the plain text without knowing the decryption key. So all cryptanalysis is predicated on the idea that you cannot gain the key, so instead you try to obtain the plain text without knowledge of the key. And so the simplest approach is, well, to guess the key. And so if you have a key that's L bits long, then it's going to take you 2 to the L-1 guesses in expectation to actually find the key that you're looking for. So this is why we see recommendations for long key bit length. So AES, the advanced encryption standard used for symmetric cryptography, uses a recommended key length of 128 bits, which means that any brute force attempt is going to require 2 to the 127 attempts in expectation to guess the key, which is 100 times a trillion times a trillion times a trillion, so it's a lot. It becomes infeasible. And so what cryptanalysts do is they look for shortcuts, so that whereas in the worst case you would expect 2 to the L guesses, if they can get that down to 2 to the K, where K is less than L, then they will feel that they have succeeded. And so what do these shortcuts look like? Well, they tend to exploit esoteric assumptions in the mathematics or in the number theory underlying the cryptographic system, or they will look for patterns in the ciphertext. So they will collect large amounts of encrypted text, and then, which is supposed to be completely random, but actually has some small cases of non-randomness if you can collect enough of that data. So here's just a simple example of how you might do this. So if you think about it, the distribution of letters in English is non-uniform, right? So, and here's the distribution. You have E is the most commonly occurring, T is second most occurring, whereas J, Q, X, and Z very rarely occurring. And it's different for every language, but if you know that the language that you're encountering is in English, then a very simple cipher, such as a Caesar cipher, where you're shifting all of your letters by 3, you can quickly observe that if the letter that you're observing is most commonly occurring, and you're looking at English, then that would be an example of what the shift is on. So like, let's say you have English, and suddenly the most commonly occurring letter in the language is F. Then it would be a good guess that the use is of a Caesar cipher with a shift of 1. So you can try that. And then this basic concept applies to even more modern types of encryption mechanisms. But obviously the sophistication is increased in terms of the statistical analysis of the distribution of ciphertext. So one thing to note about crypto systems is that it's been known for a very long time that it makes sense to publicize the algorithm itself, how the crypto system works. And instead, you should design a system so that the overall security depends only on the secrecy of the key itself and not of the operations of the crypto algorithm. And this concept came from August Kirchhoff, who first articulated it when looking at early crypto systems involving the telegraph. And the rationale he gave, which still holds today, is that it does a few things. One, it avoids blind trust, so you're not just assuming that the algorithm itself is actually secure. You are allowing many eyes to inspect the system, look for flaws. And the other thing to note is that it's much easier to change the encryption key, than to change the system. And finally, if you have to assume that your crypto algorithm is not public, then that means you need to hide this information. And so that just increases the obligation of the user of that system, and it becomes very hard if you want to, say, distribute this code that implements an encryption algorithm widely. Well, it's not really credible that an adversary won't be able to obtain the code. The way that this Kirchhoff's principle has sort of been translated into a bumper sticker is to say that there is no security by obscurity. So you cannot rely upon the obscurity of your mechanism to achieve security. And this principle applies in many forms of security engineering, so not just in crypto systems. And yet, we often see cases in which it is ignored. So here's an example of this is in the London Underground. They had a contactless payment system that would allow underground users to gain access, and uses RFID. Well, the underlying communications between the Oyster card and the reader were encrypted, but they were encrypted using something called MIFARE, which was a secret encryption algorithm. And it turns out that it wasn't a very good one, and it got hacked. And this same underlying system has led to hacks in Boston and other subway systems which use the protocol. And once the details of the underlying MIFARE protocol became known to the research community, it was immediately clear that the design was lacking. If you ever encounter someone who says they have this super secure crypto system but won't tell you the details, you should run away as quickly as you can, because they're probably a snake oil salesman. More broadly, one question that I think is worth raising is whether or not cryptanalysis experts have the right threat model in the first place. So, like I said earlier, what the goal of a cryptanalysis is to try to observe plain text derived from ciphertext under the assumption that you do not have access to the key. And why would you make that assumption? Well, if you can gain access to the key, it's game over. It's trivial to decrypt the plain text. And so a lot of the mathematicians working in this space, well, I think it would be too easy to just consider gaining the key. So they tend to focus on these breaks where it's not relying on having the key. But when you look at what happens in the real world, it doesn't actually always seem to work that way. And so this is a quote from Adi Shamir, who gave this during his Turing Award lecture, which is like the Nobel Prize for Computer Science. Adi Shamir is the S in the RSA asymmetric key cryptography system, the second one developed, the first commercially viable system, which is still in use today. So we have a world-leading cryptographer who says, cryptography is usually bypassed. I'm not aware of any major world-class security system employing cryptography in which the hackers penetrated the system by actually going through the cryptanalysis. Usually there are much simpler ways of penetrating the system. And I think this is an important lesson, especially in where we're thinking about the strategy of adversaries. And in general, it's true that most attackers bypass your threat model. And this really shouldn't be surprising, because if you've done a good job engineering your system, then it should be designed so that attacks that the engineers plan for are difficult to carry out, maybe even impossible. And so, given that reality, what happens? Well, the threat models are either bypassed because the attacker operates in a behavior that is not assumed by the threat model, or you've maybe over-engineered your problem altogether, and you've given way too much power to the attacker, and you've led to a system that may be secure, but is against a particular mode of attack, but is not practical, or is too expensive to deploy. So this is a real problem. And when we look at cryptanalysis in particular, the threat model that they use fails on both of these counts. So first of all, they're often overestimating attacker capabilities. So often the main threat actor is assumed to be a global active adversary. So somebody who can observe all communications, store them for an indefinite period of time, and has tremendous resources to try to brute force attacks. So you end up with recommendations for very long key lengths and very over-engineered systems. But then you also have this over focusing on decrypting ciphertext without access to the key. But nearly all attacks work in the real world by finding a way to get access to the key, because it's much cheaper for the attacker to do so. If you can find the key, then that gets you what you need, and you don't have to worry about having all of these extremely expensive cracking operations in place. So how do people get the keys? Well, attackers are very clever. So here's an example of a cold boot attack where essentially RAM, volatile memory, whenever you turn off power to it, the contents is supposed to disappear. And so if you have an encryption key in RAM and you turn off the system, it should go away. Well, it turns out that if you have physical access to the system, you can put the memory, turn the system off, turn it back on, and once the new user has read access to the memory, you can actually observe the leftover key. So this has been shown to be practical and completely violates the assumption that designers had. That they assume that you put a key in RAM, when it's shut off and goes to a different user, it can't be obtained. Well, it turns out it can. The more broad consideration is that the users of a system don't behave as the system designers thought they should. So a lot of the most successful attacks trick users into sharing their keys or their passwords, right? So think about a phishing attack. It's designed to encourage and trick a user into handing over a secret. And this runs counter to the way system security operates. It's predicated on entrusting the user to make the right decision and only taking actions that are in their own interest. And this is a sort of a reasonable thing for systems designers to do because it's really hard to always make decisions for users. But what this does is this offloads the hard decision of whether to allow an untrusted software to execute on a system. And so users get conditioned to eventually just accept and allow everything. And so the best example of this was Windows Vista's user account control. Every time someone needed to ask for privileged access, their screen went dark and they were presented with this request. And it turns out that 99 times out of 100, that request was reasonable and should be granted. And so users get habituated to just accepting the warning, and then the 100th time comes along and it's malicious software that's gaining access, they're going to click yes anyway, and it completely undermines the system. Okay, so to wrap up, we'll in one slide talk about the other side of this, which is how you counter security threats. So we have our castle where we're engineering our defenses to protect confidentiality, integrity, and availability. Then we have the security threats, which come in and penetrate through the defenses. And then the last step we'll discuss is how do you counter those threats. And so one way to do it would be to go back and engineer better defenses, but another way is to try to take the threats head on. So yeah, when weaknesses are discovered, you have two choices. Go back, build a stronger castle, or deal with the attacks directly, defend against the attacks directly. In the long run, you may be better off making fundamental changes to your defenses, but in the short run, you have to do something else. And so that's where the response to attacks comes from. And it really can be characterized into two main categories. One is an ex post countermeasure, where you wait for the attacks to occur and you intercept them and prevent them from causing harm. So this is what an intrusion detection system does. You place it on your network, you observe attempted attacks and block them. This is what antivirus does. It sits on your computer, inspects all of the programs you execute, and tries to block them if they know that they're bad. But there are also ex-ante countermeasures that you can do before an attack has occurred. And these are things like penetration testing, where you're trying to find weaknesses in your software or in your organization's system configuration before an attacker does. And so security audits work in a similar way. So that is going to wrap up our discussion of security threats and how they're countered. Thank you for your attention.